Welcome, everyone. Thanks for joining us. My name is Marisa Gomez. I'm the Public Programs Manager at the Santa Cruz Museum of Natural History, and we are excited to bring back the Rockin Pop-Up once again, our weekly program that we have with the Geology Gents, Gavin and Graham. So I'm going to welcome in one of the Geology Gents, Gavin. Hey, Gavin. How you doing?
Hey, Marisa. I'm doing well. How are you doing?
So good. I'm happy to see you today. And you're all by your lonesome right now, but I do hear that you have a special guest. Is that true?
That's true, yes. So today we're doing an interview, and the reason we're doing the interview is because we're trying to take the audience through the life and journey of a scientist, specifically a geologist. So I have a really special guest today. I'm really excited to welcome him and to talk science with him.
So, hey, Gavin, it's good to see you.
Hey, Graham, thanks for coming on the show today, and I'm really glad I get to interview you.
Oh my goodness, my pleasure. Big fan of the show. Really excited to be on today.
Oh, well, I am very excited to have you. And so, as I mentioned, today we're gonna be bringing to the audience what it's like to be a geologist, and we're going to be going from your journey up until now to get to your PhD, and then what it's like getting your PhD, what are the timelines of your projects, and the types of things that you do on a daily basis. So does that sound good?
Sounds great. I can't wait to sort of help folks get a peek into the life of a scientist. This will be fun.
Fantastic. Okay. So as I mentioned, I want to pretty much bring the audience on your journey as a scientist. So can you just briefly share with us all how you got to become a PhD student in STEM and how you decided to be a geologist in general?
Yeah, I'd love to. It's so the journey to becoming a geologist started all with when I was young. I just loved. I was very curious with the natural world and natural history. I loved going to natural history museums. I loved, looking at the skeletons of animals, looking at fossils, loved to see the rock and gem collections. I loved going and collecting bugs and rocks and twigs and leaves when I was a kid. And so I always kind of knew I wanted to be a scientist in some natural science. I originally thought I would probably go into biology. I was really interested in animals and critters. But then when I was in college, I took my first geology class, and I just loved going and looking at rocks, being able to interpret the world around me. And I really just got hooked there. And so in that moment, I sort of figured out what my science would be. And I've been doing it ever since. It's been a great almost 10 years now.
Oh man, well, we're just really, really glad to have you in the science community, Graham. And I feel like this is a good time to remind the audience that the difference between just a curious person and someone who does science for a living is just their career choice. And the idea of that career choice for you might have been you always kind of knew you were a scientist, but it just took like a couple of classes in undergrad, right, to get you hooked into geology. And so really everyone can do this, and it's just a matter of like finding what you're curious about. Would you agree, Graham?
I would totally agree. I think we're all scientists at one level or another, whether we just do it for fun on the side or we decide to make that a career out of it. And so, we all engage in science at however much we like to or have at our disposal. And so I think being a scientist is really a state of mind, and I'm grateful that I get to do it so much of the time.
Totally. Yeah, I like that. It really is a state of mind. Okay, that's great. So now that we've gone through your journey, can you describe, we all know that you're a geologist, but can you describe what your specific title is as a scientist and what that might entail?
Yeah, I'd be glad to. So I am a geochemist. So I am interested in the chemistry of rocks and other geologic materials, whether it's sediments or waters or things like that. And more specifically, not only do I like to use the chemistry of geologic materials to understand something about Earth history, I am also a geochronologist. So chronology being coming from the Greek word chronos for time. And so I'm interested in geologic time and measuring and keeping track of geologic time and using that to understand when and at what pace events have happened in Earth history.
Oh, Graham, A, great answer. B, I love how you always find the roots of the words and how you know that. Words just make so much more sense when I talk to you. Okay, so geochronology, you use chemistry to find time. That's great. And so can you describe to me how it is that you go from a rock, though, and you get the time out of it? How do you get the date?
Yeah, so that's a good question. And there's a lot of different ways that folks do this. What they do is, or at least in my case, I rely on isotopes. So I've got a little chemistry primer here for folks, and hopefully it's not going to, it's not going to be too upsetting to dive back into this realm of chemistry. It's not always a happy memory for folks, but I think, we can hopefully here we can just take a bite out of chemistry and really enjoy it here. So all that really matters as far as we're going to go into this is thinking about elements and isotopes. So elements are the different types of atoms we see on the periodic table, and isotopes are different sizes of a specific type of element. So probably the isotopes we're most familiar with are carbon isotopes. We use those in carbon dating or radiocarbon dating. And it's this heaviest natural carbon isotope, carbon-14, that's radioactive. And so it decays radioactively through time. It's a very precise clock. And that's the same reason we have things called atomic clocks. Atomic decay is a great way to measure and keep track of time. And so carbon is a very light isotope. It's a small and it only has a few protons and neutrons. I'm interested in using uranium. Uranium, there's a picture or a diagram of it here, big, lots of protons, lots of neutrons. And uranium decays to lead over long time scales. And so as geologists or as geochronologists, we use uranium as the way you can think of it as uranium decaying to isotopes of lead as like sands in an hourglass, right? So we start out with all of our uranium up top, that's our parent, and it's gonna drain down through time and fill in the lower part of that hourglass. And we know how much time has passed by measuring how much uranium is still up on top and how much how much lead has accumulated at the bottom. So that's the way that as geologists can measure dates. But I'm going to throw one other word in here at you. So we can use radio decay to measure the age of things, but then if we measure the ages of multiple things, then we can actually tell how much time has passed. And that's where we get this term that geochronologists love to throw around, rates and dates. Dates and rates. And so by measuring dates, we can determine how much time is passing. We can get those rates of geological processes. And so by putting those two things together, we can really start to understand the tempo of processes in Earth's history.
Okay, Graham, that makes a lot of sense. And it kind of harkens back a little bit to last week when we were talking about some of the greatest hits of geology, how we know the dates of those greatest hits, and how we can put those times on a timeline. So you're doing exactly what those past scientists were doing that we talked about last week. Is that right?
That's exactly right. Yeah, trying to help put these processes into the context of when in Earth history.
Cool. Okay. And so that's basically your approach to a scientific question. You have some date and you're trying to figure out what that means in terms of how the world was during the time of that date.
Yeah, that's exactly right. And as scientists, we often call these models. It's an idea of how the system is working. And we keep track of some things and we kind of ignore some other things, but we use those rates and dates to come up with an idea or a model of how things are changing in Earth history. Yeah.
Cool. Okay. So that makes a lot of sense. So I have a good idea now of why and how you use the dates. But I'm really curious though, like, do you just how do you find I know you measure the uranium, but like do you just take a rock and you put it in some machine and that machine measures the uranium? How do you know how do you go from rock to date?
That's a great question, Gavin. And this is some of the smoke and mirrors of science here, right? This is we talk about going into the lab and all the things we do there. And so here's an opportunity. I'll take you sort of through a day in the life of a geochronologist, or some of the things I might do in a day in my life, and take you through the process of measuring a date.
Awesome. Yeah, let's look under the hood. I want to see how the sausage is made.
Great. And so here's a picture of me in a lab working with a rock. This is a big block of dirty ice, and that's not exactly what I'm going to talk about here, but this is me in action, but I'll take you through some of the steps. So we often start with some rock. And a lot of folks come here because they're interested in rocks. So I'll tell you how we date a rock. So you take a rock and you need to break it into little pieces so we can separate out the stuff we want to measure. So these are some rocks that are crushed down. They start as chunks and then they end up as this powder. And then with that powder, we separate out the minerals we're interested in. So some minerals, some bits of that rock are magnetic and some of them are heavier than others. So we use heavy liquids to separate out the heavier things from the lighter things. And then we use this funky machine over here called a Franz magnetic separator to separate out magnetic parts of a rock. And you may say, Graham, rocks aren't that magnetic. And that's true. Most of rocks that we hold aren't magnetic, but there are parts of them that are. So I've got a little video here showing you just that. I'm going to reach over this rock with a magnet and woo, look at those little magnetic minerals zip up to it. And so we'll do these to separate out the parts of the mineral that we're most interested in. And that's what I've got over here. These are some phosphate minerals that I tried to date once. And then we take those and we dissolve them in any sort of, oftentimes it's an acid or some sort of chemical that'll help break down those solids and get them into a liquid, get them into a salt in the water. Here are some beakers that have some rocks that I've digested in there. And then we purify out those elements we're interested in, right? We don't need the sodium and the potassium and the calcium and the magnesium. All we want to know is that uranium and the lead. So once I get those purified out of there, I take them and I put them onto a mass spectrometer. And we mentioned that very briefly. And these are big, fancy machines that we use to measure isotopes. And that's as far as I'll go into that. But this is kind of what the screen looks like. And so we're trying to measure a signal and we're trying to measure the amounts of isotopes. And this is actually showing us two different isotopes that we're measuring at the same time. And the amounts of those sort of going up and increasing with time.
Wow. Okay. So you've brought us full circle, Graham. You mentioned that the way we date rocks is with the isotopes, and then you took the rock, you crushed the rock up because there's a specific mineral inside that rock that you want to date. And so why did you pick that specific mineral? Real quick, could you just describe that?
Yeah, that's a great question. So different minerals, because of the chemistry of those minerals, they'll hold certain types of elements in them in different ways. And so I went for that mineral phosphate because phosphate loves uranium. And so it loves to take up a bunch of that uranium. And so by finding that, I get something with lots of uranium in it. You can think of that as something that started out as a really full top of the hourglass. And so all that lead that we can measure in there is recording all that uranium that has decayed in there through time.
Cool. So yeah, it's just an easier measurement when the mineral has a lot of uranium, right?
That's right. That's right.
That's awesome. Okay. So this seems like a lot of steps, Graham. So you go from rock, you crush it, magnetic separation, all that stuff, dissolve it. Can you describe the timeline of, well, first off, can you describe the timeline of that process? Do you do that all in one long day? Like, can you describe that?
I wish I could knock it out in a day. No, these takes days to weeks. It takes a long time to do these, and you want to be really careful that you do them carefully and do a good job with each step of the process, because that really helps, give you a good high quality measurement at the end. And so in sort of any given day, the lab work I'm doing is juggling, one or a couple of these things and trying to, slowly and incrementally get to the making measurement phase. So I spend a lot of time in different sorts of labs, whether I'm crushing a rock or separating out a mineral, or working in the clean chemistry lab, just getting out those uranium and lead atoms.
Interesting. Okay. And so when this is a kind of a good time to remind the audience that when we call ourselves geologists, it doesn't mean we're trouncing around in places that look like our background every day. Unfortunately, most of your day, you maybe get to go to an outside outcrop to a rock once every, say, year or so, but most of your time is spent in the laboratory making measurements, gathering data. Would you agree with that?
That's right, but there's one other thing that I didn't cover in this, and that is that I spend a lot of time making measurements. I spend a lot of time, collecting data, but half of my time is also spent doing this other thing, and that's, thinking about the process, trying to understand those data in the context of a model. And I never really covered that. So to sort of unpack that a little bit, the process of thinking about the science, the geology, the earth processes, I've actually brought on a special guest today who I'm really excited to interview and talk about this. He's a brilliant early career scientist who's been working in this field. Folks out there, please give a warm welcome to Gavin Piccione. Gavin, thanks for coming on the show today.
Oh, Graham, I'm so happy to be here. I feel like I've been here the whole time.
Oh my gosh, it's funny how it feels like that sometimes, right? I'm glad you can make me feel so welcome. So, Gavin, I've got a lot of questions for you today about the process of doing science. Earlier we've talked a little bit about collecting data, the lab part of science, but I really want to hear about getting into the thinking and the unpacking and solving a scientific question. But first, I want to know, how did you become a scientist? What got you to being a PhD student studying geology?
Oh, fantastic question, Graham. So, okay. As far as becoming a scientist, I kind of like you was always curious, kind of human nature to be curious. And as a kid, I was always outside, and I really took a liking to natural processes similar to your background as well. And I do have to shout out to my parents here as well, because as soon as they saw that curiosity in me, they were really encouraging. And they too, they weren't scientists themselves, but they thought science was interesting. So they were encouraging me to keep going and to keep exploring. And as soon as I got into rocks, that was it. I was sort of a mineral fiend since I was a little kid. And so when it came down to trying to pick my career and trying to pick what I was going to study in college, I decided rocks were the no-brainer. And that was, 8 to 10 years ago. And I just kind of kept going with it. And so, that's my story.
Oh, I love it. And how lucky are we geologists knowing that we've got you around among us now. Glad to have you, Gavin.
I'm glad to be here.
So you're a geologist. Can you tell me a little bit more about what kind of geologist you are?
Well, okay, I could do that. I hate to bore the audience, but my title is almost exactly what Graham's title is, and it makes sense because we work in the same lab. But I'm also first and foremost a geologist. I am driven by understanding geologic questions, and the way I do it is also with chemistry. So I'm a geochemist. That's the title for that, and I also use dates to understand things in the natural world. So also a geochronologist like Graham. And so the thing that distinguishes Graham and I is sort of in the minutia, but the types of geologic questions we look at are a little bit different, but we both use geologic time to get there.
Yeah, I love it. And it's great having, someone whose head's in the same sort of space to be working with in the lab. And of course, that's why we're lab mates. We do similar stuff.
Totally.
Not exactly the same. Keeps it exciting. So, okay, you've talked about what kind of stuff you do, but we talked about the processes we go through, right? Finding something to date, pulling the thing out of the rock to date or the geologic material, kind of the chemistry that goes into that. But what I'd really like to know is, how do you know what to date, and what do you do with the dates after you measure them?
Well, Graham, that's a really good question, and it kind of hits right to the general point of science, where it's what's the process of science. So the fact that we date something is always a means to some scientific conclusion, right? So we're trying to draw a scientific conclusion, and we have a hypothesis that supports that conclusion. And so the dates are the results of experiments to test that hypothesis. So I have a geologic question I want to answer, I'm curious about, and the way I answer that is with the dates. And so, Graham, it might be good to give a little bit of an example of this, right? To make it less abstract for the audience, right?
I would love to hear an example if you've got one for us, Gav.
Fantastic. Okay, so I'm going to share screen here because I also have a couple of pictures to share with everybody. So can you see this, Graham? Okay, gotcha. Okay.
Sorry. Yeah, that's beautiful. What's going on there, Gavin? Sorry, I muted myself.
No worries. Okay, so I mentioned that the dates are a means to get to falsify a hypothesis, to figure out whether your hypothesis is true or false, and to get to some scientific conclusion. And so this often starts with an observation. A lot of times geologists have an observation either in a single rock or in some rock outcrop or some phenomenon on the earth that they want to answer. So this is a rock I'm actually working on right now. It's a hand sample. We call it a hand sample because it fits in your hand. So it's a rock, 15 millimeters. It's pretty small, but it looks kind of weird, right? It's not like a lot of rocks you might find in Santa Cruz or normally, and that's because it comes from Antarctica. And specifically, it grows underneath the ice in Antarctica. I won't get into many of the details, but I had this observation that I wanted to figure out. I observed that the rock looks like it has stripes. And those stripes you might see here, you have white stripes, then black, white, black, and then some more white up here. So my observation was this thing's striped, and my hypothesis was, well, I think those stripes are changing chemistry beneath the Antarctic ice sheet. And so I decided to date this specific rock because I wanted to try and see if my hypothesis was right. If these different minerals that look like stripes in this sample are the result of some changes beneath the ice sheet in Antarctica. And I used the ages of the rock to help me try and find that. So that's how I figured out what I wanted to date and why generally geologists want to date things.
Awesome. Very cool. It was really great riding along for that, the process of that. So my next question then is, after you decide what you want to date or what you want to measure, you collect those measurements, and then you put that together and process it. So what's the final product of all that work? What do how do you discover something, and then what do you do with that scientific discovery?
Well, Graham, that's another really good question. So again, we're trying to make a discovery. We are running experiments with our ages to try and draw scientific conclusions. So we take the ages, we take the dates, and we want to make what you alluded to, a model that sort of describes what those ages mean for the time when that rock was forming. So just to take the audience through some of the data from that rock real quick, just because I want to show them what it looks like. So I'm going to share my screen just one more time, or for a second time at least.
Yeah, great. Oh,
Okay,
beautiful. So
you see
what you got? What's going on here?
Yeah, so these were the results of the ages of that rock I just showed. And so this is sort of, it's not exactly your question because you asked about the final product, but this is an intermediate step where we take the age and we do some math or we do some statistics and we figure out if those ages are correct. And then we build a model to describe what those ages mean for the time, and then we use that model to test our hypothesis. And so the end result is me being able to say if I was correct in that those stripes in my sample actually mean something about the Antarctic ice through time, and more generally, whether my hypothesis was correct and I could draw some scientific conclusion from it.
Awesome. Very cool. So you're working through to get to some new understanding. So hypothesis, testing hypothesis, conclusion, these all sound familiar to something most of us probably learned in a science class at one point in our lives, and that's the scientific method. So Gavin, everything you're putting together here, it sounds like this is all part of this sort of model that we're working on. And I don't mean a geologic model, but a way that we address the problems called the scientific method. Can you tell us what that's all about?
Totally, Graham. And I have a slide for that. So the scientific method, something a lot of folks probably have heard of in a high school science class or a college science class, but it's exactly the process I was describing. And so the scientific method isn't just something that we use to pass a lab in high school. It's something that scientists like us are using every day, where we're doing exactly what I was describing. We're finding a question, whether it be some observation we're curious about. We do some research. We try to figure out like what the answer to that question might be. We have a hypothesis. That's a buzzword where we make an educated guess. We try to figure out the answer to our question, and then we test it with our experiment. And this is where the dates come in. So the experiments for us are trying to find the ages, and the ages are what we use to test our hypothesis. And then we try to get some data and draw some scientific conclusion to where we're done, where we figured out what the answer to our question is.
Okay, cool. So that's the scientific method. For those of us who had seen it before, hopefully this was a good refresher. For those of us seeing it for the first time, hopefully that's, kind of makes sense. It's a good way of tackling a problem. So it seems like it's all pretty cut and dry. You pick a hypothesis, you test it, conclusion, and that's the end of that. Is that how the scientific method works for you as a scientist?
Oh man, Graham, I just wish it was. It would make my life so much easier, but I guess it would also make my life a little less interesting. So no, it's not how it works. It's not just one hypothesis, some data, make a conclusion, write a paper on it, call it a day. That's not how it works. I would say that a lot of what I do in my daily experience is find new hypotheses and test them. So once we get the data as scientists, we are oftentimes find it surprising or it doesn't exactly align with our hypothesis. So we have to go back, look at the data set, figure out what that means, test it again. And so one scientific conclusion is usually the result of testing a hypothesis 10 times, 100 times, but a really, really long time. So it's an iterative process, what we call it. We're sort of finding it, we go back, we test it again, we see what our data set is telling us, we use that to go back and test it again, get more data. And finally, when all of it's said and done, we have a result that can draw some conclusion to our question.
Oh, that's great. It sounds exciting. And when you describe it, Gavin, that also sounds kind of familiar. The scientific method is something a lot of people use in any day, right? Like we use it as scientists and we call it the scientific method, but it doesn't just have to be, a geochronologic question that we apply it to, right?
Yeah, that's exactly right. And the scientific method might seem scary or like something that is not really accessible just because we have this like well thought out framework. But if you really think about it, it's just careful problem solving. It's making an educated guess, seeing if that guess is right. And so I'm sure what the audience is thinking is, yeah, I kind of use this sort of a similar method in tackling daily problems and, daily curiosities.
Yeah, and I think, that kind of comes back to what we were talking about earlier, right? That like we're all scientists in our own way. And for some of us where, chewing on that science is what keeps us going, we have sort of latched on to the route of being a scientist, but being a scientist really is, it's a way of just looking at the world or looking at whatever problem you have before you and thoughtfully trying to make sense of it.
Yeah, that's great, Graham. And I think that's a really good place to leave it. That makes a lot of sense to me.
Well, Gavin, thank you so much for coming on the show today. It was really a pleasure talking to you.
Oh man, Graham, I had a great time, and thank you for also being such a good interviewee as well.
Oh, you're too good, too nice.
Well, thanks for that, guys. I'll peek my head back in now, and maybe ask a question myself of you two scientists, which kind of has to do with what you were just closing with on the scientific method. I'm curious about your ability to use tools to answer those questions that you have. So you have a hypothesis, you get some data, you analyze it and determine if it supports your hypothesis or doesn't, and then you maybe have to go back again. So I'm curious about this, getting that data part. Do you ever find yourself up against a wall where you don't have the tools you need to get the data that you would like to have in order to answer your question? And do you ever find yourself problem solving in that realm? Do you ever find yourself coming up with inventive ways to get the information that you need? How much of that has to do with you doing science?
Marisa, that is actually a very good question. And I see Graham grinning because this is sometimes something that him and I lament on a lot. So the thing about our line of work specifically is that we are geologists, so we work in the rock record, which is oftentimes very sort of incomplete, and we don't necessarily always have the exact rocks we need. And then the other side of things is we're chemists who work with these big machines, or instruments, I should say, that are very expensive, but actually don't always run like you would want them to run. And so I would say that a vast amount of time we are actually trying to get the measurements right, trying to make sure that our data is correct and that our data is the best that we can make it. So we're geologists, but we oftentimes find ourselves doing a lot of statistics and math because we have to be data scientists as well. And so maybe even a majority of the time we are troubleshooting, finding better ways to do things, finding just general ways that will work to answer our questions. Definitely. Do you have anything to add to that, Graham?
Yeah, you've hit the nail on the head there. That nature is complicated, and if nature were simple and easy to figure out, we wouldn't need scientists. We wouldn't need geochronologists to work on these questions and understand these things. And getting at those measurements is also tricky. Like Gavin said, our instruments, they're very special, high technology tools, but they also they don't always work. And so oftentimes we are testing hypotheses of trying to fix how to make a measurement because something may not be working right, or we don't have just the right rock. So we're trying to make the ones we have work out, as best we can.
I'm thinking too about people who don't have the instruments that you have, and how you did relate the scientific method to everyday problems, and also for all of us as scientists or naturalists out in our own little worlds making our own observations, that we may not all have the same tools, but we can still ask questions of what we are exploring, develop our own tools. And then sometimes though you do need to kind of take it a step further, and I think that kind of maybe brings us to next week's theme a little bit to me, and how you guys have taken your studies of rocks beyond collecting a rock, looking at it closely, figuring out how to tell if it's metamorphic or sedimentary or igneous, which we've covered in previous pop-ups for those of you watching, if you want to go back and refresh yourself. But eventually your questions get a little bit more complicated, right? And then what do you do?
Well, that's exactly right, Marisa. And so the point of having these big instruments and these sort of specific ways of tackling a scientific problem are that we want to always be sort of pushing the edge of what we know about the world, right? We want to be answering questions about the Earth that we might not have the answer to. So there's a lot of our whole point as scientists, or our end goal, is always a new discovery. We want to figure out the way the world was back in time. And so that, you're right, that is a good segue into next week, because next week we're going to be talking about the process that academics go through to sort of get their conclusions out to the world. And so oftentimes you'll hear us talk about writing papers or manuscripts. So we have to find discoveries that we can defend, and once we do that, we write them into papers that the community at large will look at and draw knowledge from.
And sometimes, as we're researching and studying things, we run into roadblocks that aren't just technology roadblocks or having the right tools to make a measurement, but also times where we're realizing that, we don't understand something quite as well as we wish we did. And so then we find other experts on it, and we go find folks who are very knowledgeable in a subject that we don't know very well or that we're trying to explore, and we can ask them for help too.
Cool. So I'm really liking this, where we are building our foundation of understanding rocks. We're thinking about how to look more closely at them and ask more difficult questions, which you guys covered today. And then next week, we're going to be diving into the meaning of all that and what we can do with it, and what those next steps are using a system like maybe academia, which you guys are currently involved in. So for all of you watching, we will get back into more specifics about, certain types of rocks and helping you hone your observational skills for the rocks around you. But also, this is a really important piece of the puzzle, I think, in communicating science and learning how science works, so that we can all become more educated. So I'm really excited for this this brief detour away from the physical specimens. So thanks for offering that for us, guys. And again, if y'all have a rock you want identified, Gavin and Graham would love to take a look at it. Send us a picture. There's a link somewhere in the comments here that you can go to, drop a picture, and we'll look at it next week. So thanks, Gavin and Graham, for being here, and we'll see you next week.
See ya.